Manufacturing considerations in design. Product design, selection of materials, processing materials into finished components, these are closely connected, are closely related to each other. Manufacturing can be considered as processing the available material into useful components, that is product. Types of manufacturing process, mostly we follow casting, deformation, material removal. Deformation is forging or related. Material removal is machining operations, turning, milling, broaching, grinding, drilling, etc. So whereas joining, so this can also be considered as manufacturing process like riveting, welding, etc. So first we will focus on the three: casting, deformation, and material removal. Here you can see key components in the engineering application, how they are made. So first we start with the connecting rod. The connecting rod can be manufactured by the forging, the deformation, and the flywheel can be manufactured by casting, and the housing of the gearbox can also be manufactured by casting. Keys they're done by the material removal or machining operation. Bolts and nuts again by machining operation. Crankshafts they are done by the deformation or forging operation, whereas machine tool bed by casting. So here we have seen some key components in the engineering applications. They have used the different manufacturing process. So the selection of these different manufacturing process for a particular component will depend upon the things like cost of the manufacturing and the material of the component and geometric shape of the component, surface finish and tolerances required, and how many volume, how many you are going to produce. So on these 5 parameters the manufacturing method will depend upon. Suppose if you have taken the casting, casting is again done by different ways. Sand casting is the most basic method, and then shell mold casting and permanent mold casting, die casting, centrifugal casting, investment casting. So even if it is a casting, there are different methods of castings, and for the product which we want to manufacture, one of these casting processes can be adopted depending upon the above 5 things required, whether the material, or what type of material we are going to use, and how much is the volume, and what is the complexity of the shape, etc. The advantages of sand casting: this is the first method of casting, and the tooling required is relatively inexpensive and very simple. So this is very cheap, because the tools required are very simple and they are inexpensive. Therefore the total cost of the production is also very cheap, very economical. Almost any material can be casted. So you can do it for iron family, or aluminum, or copper, bronze, or even plastics can also be done by this casting. So there is no limit on the size of the component. Practically there is no limit. You can start from a component weighing few grams to a component weighing several tons can be done by this. The disadvantages: close tolerances cannot be achieved. The casted components required additional machining and finishing operations to get the close tolerances. Either the surface finish or tolerances required can be achieved only after doing additional machining and finishing operations. So that increases the cost. So the sand casting, yes, it is very economical and very cheaper, but due to the additional requirement of the machining and finishing operations, the cost of the component tends to go up. So the casted components have rough surface finish. Not only tolerances, the surface finish is also rough. We need to make it smoother as per the requirements by again using some finishing operations, starting from grinding to honing, lapping, etc. Components with long and thin sections cannot be casted. Yes, practically there is no limit on minimum and maximum size, but there are certain care and precaution should be taken while casting the product. Long and thin sections cannot be done by casting, because the hot metal has to move in the cast cavity, and if it solidifies in the long and thin sections, it cannot pass to the other end. So therefore the long and thin sections cannot be casted. Next, deformation, forging. Deformation or the forging operation is the predominant of the deformations. So out of that forging, drop forging accounts for 80% of the components made in industry. And there are other forging operations like hand forging, press forging, offset forging. The advantages of forging. The forged components have inherent strength and toughness. We have seen the other day, the strength, that is the amount of stress that is needed to fail the member, and whereas toughness is the amount of energy that is absorbed by the member before fracture. So this is talking about stress needed to fail the metal. This is talking about energy needed to fracture the material. Next, optimum utilization of the material. So in the forging, there is no wastage of the material, so therefore we are going to use the material in the optimum manner. So this can be done for thin sections without compromising on the strength. So you need not compromise on the strength, you can do it for very thin sections also. Close tolerances can be met, that reduces the metal removal during the final finishing. So when we are doing forging, when tolerances or surface finish are very close to the requirement, so therefore in the finishing operations you don't need to remove the materials to get to the required size and shape. Relatively rapid production rate and good reproducibility. So it's very fast. The forging operation is very fast, and hence you can use it for mass production, and the reproducibility is very high. That means the component made as 100th one, component made as 200th or 300th one. So all these are pretty similar, and there won't be any deviation from one another. There are certain disadvantages. So the equipment and tooling are costly. So it cannot come with all the good things. It comes with some expensive things. So the expensive things are the equipment and tooling. It is economical only when manufactured in the large scale. So because of this overhead cost, the establishment cost, if you are able to produce things on large scale, then only it will become economical. Otherwise, the parts manufactured by forging operations will be very, very costly. Next, metal removal or cutting process. So this is most versatile and common manufacturing method. Almost every component subjected to some kind of machining operation before its final finishing stage. So most of the things, whether they are casted, whether they are forged, etc., so they need some kind of machining operation, whether it is for final finishing, that means grinding or honing like that, or whether it is bringing it to the required size or surface smoothness, etc. So therefore it is essential after other types of manufacturing process also. There are several metal removal operations. The first one is metal cutting process, and second one is grinding process, and third one is unconventional machining process. So metal cutting here, if we have taken a bar of this magnitude, let us say diameter is 70 mm and the length is 1 meter, and if you want to make it to 50 mm diameter and the length is 800 mm, then we need to turn to the 70 mm to 50 mm and 1 meter to, that is 1000 mm to 800 mm. So this way we need to machine, and this way also you need to machine to get the final shape of the product. And grinding, this is used to get the required amount of surface finish. In the ordinary metal cutting operations, you are not going to get a very good surface finish. In order to get the good surface finish, you need to go for grinding process. So the grinding is the basic finishing operation, and on the top of this you will have several other finishing process, and next is unconventional machining process. So using the unconventional machining process, we're going to get the final shape of the component, but it takes a little bit of more time, and the equipment are expensive, and the time taken as well as the cost involved is more. Therefore the unconventional machining process cannot be used for mass production. So the metal cutting and grinding, so these are used for mass production, and the unconventional process can be used for the complex shapes, or using materials which cannot be cut by using ordinary metal cutting process. So when the materials are hard or the shape is complex, and then you can go for unconventional machining process. The advantages of machining process: almost any metal can be machined in either first, second or third. You can do it depending upon that you are going to change the tool. So for different materials we are going to use different tools for the cutting operation, and it is possible to achieve close tolerances. That means the required size is suppose 50 mm, you can go up to 50 mm on higher side or lower side. So that tolerance is within the allowable zone. If you want to make it a diameter 50, so you can get very close to that, 50.001 or 49.999. So this is the tolerance zone. If you are going to make within this zone, that is within the closed tolerances. Machine components have good surface finish. So these machine components not only having the dimensions close to the requirement, but also the surface finish is close to the requirement. Good surface finish can be achieved. Disadvantages: so the machining process requires machines, and these need power, and these need operators, and these days we are using CNC machines, and CNC machines are more costlier to procure, and therefore the total cost of the operation is costly, and rate of production is low compared to casting forging. So however, the rate of production, because of the loading the component and operation is done and removal of the component, all these things will take certain amount of time rather than the actual machining operation. So therefore it slows down the rate of production. It's not possible to machine thin sections or projections. So again there is a drawback, very thin sections cannot be machined. So there is significant wastage of the material during the metal removal process. So in order to get to the required size, either in the dimension or the cross section or the length, we're going to remove the material. That means the dimension is made smaller during the metal removal process in the form of chips. So that is going to have a lot of wastage. So the design considerations of castings. We know that the casting has casted products are having compressive strength greater when compared to the tensile strength. So when compressive strength is greater and tensile strength is smaller, the casted components must be seen that they are subjected to compression rather than they are subjected to tension. So if you have taken a product which is made by casting, instead of loading this way, here it is fixed with the help of 3 bolts, and here we are applying a load. So therefore this is subjected to tensile load. So this is not good. Instead of that, it is placed here and load is applied here. That means there is a shaft or something is going through this, and the load is acting in the downward direction. So therefore this member is subjected to compressive load. So because the casted products are having higher compression strength, therefore it is better to use this way rather than this way. This is wrong and this is right for casted product. And the other design considerations, here also in cases where the tensile stresses are not avoided or cannot be avoided, like this, we are going to use a tie rod. So these are the 2 ends. You need to apply a force like this. That means a tensile force applied, it is pushing this way and this is pushing this way, and hence this entire member is subjected to tension. So in this case, you have to have something called a tie rod. So here is a bolt and nut assembly is used to connect these two, and they are applied with forces. So they are going to minimize the chances of failure of this casted product from the tension failure. Another way of doing the tension failure for the casted product is using a bearing cap. So this is a bearing cap. This cap is going to encapsulate the 2 ends of this casted product, and when you are applying a load, this is resisting the tensile force applied on this member, and hence here also the tension failure is avoided. So instead of having these sharp corners in the casted products, it is better to have the rounded, so that the molten metal flows through easily and it solidifies. So in these cases it goes this way, and these areas will not be subjected to the filling of the metal. So this is the area and this is another area. So there will be defects in casting. If you are going to do this, so here the smooth edges, the molten metal will easily pass through that, and when it solidifies you will get a sound casting. So the edges are here in the T section. Here also, when the flow is going to take place, here also, when molten metal is entering this way, so this area and this area, so if it is entering this way, this area will become the defect. So this area and this area will be subjected to defects in casting. So when you make this way, the rounded the chamfers, then it can flow easily, and when it solidifies there won't be any defect, no defect. Here defect, here also defect. So here you can see again the sharp edges and the section is long. You can see this section is long and this is thin and there are sharp edges. So for having such long sections with sharp edges is very disastrous by using cast. Therefore we are using the curve, so that the flow of the molten metal will be done either by this way or the other way also. So much better option is this. There is a curve and this is much better way, the best possible way. So there is a taper, so that material can flow very easily, and when it solidifies you will get the best or sound casting, sound product. Any concentration of the metal at the junction is the same, likely to result in shrinkage or a blowhole. Here you can see so here you can see the after metal solidifies, and these are the areas of exposure to the external surface, and when it gets solidified, the here this part is not subjected to any exterior circumstances. So when this is exposed, they will get cooled first, and during the shrink, for shrinkage they are going to draw the material from the center. So when they are going to draw the material from center, there will be a tendency to develop a blowhole or air gaps at the middle. So it is better to do this way. At the center, if you are able to provide poured holes, then the above mentioned the blowholes can be avoided. This is good, and here also you can do that. The curve, when you are providing, then this part will be free from blowholes. So here also you can see the ribs they are provided, rather than providing them on one side, they are provided on both sides, as well as there is a curve provided for the extended part. So what we need to do, we have to avoid thin sections, and the thickness, if it is small, and should be increased so that it can be properly casted. In general, the minimum thickness for grey cast iron component is 7 mm for parts up to 500 mm long. Up to 500 mm long, the minimum thickness is 7 mm. So there must be greater than 7, it cannot be less than 7. Short blast the parts whenever it is possible. So this significantly increases the endurance limit, particularly in case of thin sections. When you are making casting for thin sections, the short blasting the parts will increases the fatigue strength. When endurance limit is high, it will have greater fatigue strength. That can be done only by doing the short blasting. So design considerations, here you can see when two plates are joined like this, if this part has to be casted, and these two are joined with the help of a bolt, and this is coming very close to the outer edge, so this is poor. And when you are providing maximum material this way, so this is good. And when you are doing this, when you are joining these two this way, so this is much better. Uniform wall thickness. And casted product with a hole like this, and it results in stress concentration at this section. The material for resisting the applied load is smaller, and hence this area is subjected to highest stress concentration. Stress is more, and when you are doing this this area and this area, all these areas are very nominal changes. So there is a small area is reduced. That means the holes are provided in the casting in such a way that they are parallel or in line with the application of forces rather than perpendicular to the forces. Here you can see even though the curves are provided here, the parts are subjected to some kind of problems here. So it is better to have a taper like this. When you have taper rather than the vertical edges here, so the molten metal can easily flow, and when it solidifies there won't be any defects. This is the correct way of doing and providing taper, and this is a slightly incorrect way. So here also you can see this is the incorrect way of casting, and this is a better way of casting. So the outside bosses, you can see here the bosses are outside, so these are also outside. When these are eliminated, so then it is better. So the summary: always keep stressed areas of the parts in compression, and round all the external all the external surfaces or corners should be rounded. Whenever is possible, the section thickness should be kept as uniform, and avoid concentration of the metal at the junction, and that is which will result in the blowhole or shrinkage cavity. Avoid very thin sections. Short blast the parts whenever it is possible to increase the endurance limit, particularly in case of thin sections. Right. ఏంటమ్మా